Hello, so today I'm going over a system on chip that I designed in college that's able to communicate with the user via a universal asynchronous receiver transmitter, also known as UART, interface. It's also capable of interfacing to memory. Now, in order for the SoC to be able to accurately communicate with the user and vice versa, they both need to set up an agreed upon communication scheme. The available formats for my designed SoC are 7N1, 701, 7E1, 8N1, 801, and 8E1. The first letter corresponds to the number of data bits that are being sent. The second letter corresponds to the parity of the communication type, which can be no parity, odd parity, or even parity. Finally, the third letter corresponds to the number of stop bits that are going to be sent through the design to verify that all of the data has been received. The baud rates supported for this SoC include 300, 1200, 2400, 4800, 9600, 19200, 38,400, 57,600, 115,200, 230,400, and 460,800. The devices used to facilitate this communication are the Digilent Nexus 2 circuit board and a terminal window. Here is a top-level diagram of my projects. It consists of 5 major code blocks. The first major code block in the system is the asynchronous in, synchronous out, also known as AISO synchronization circuit. The purpose of this code block is that it makes it so that the reset button on the Nexus 2 board, which is generally high active, generates a low signal every time it's activated. This is because all the reset logic in the system, excluding the PicoBlaze, is low active. The output of my AISO block goes into all the other blocks in the system. Because the PicoBlaze is a high active reset, I need to invert the AISO output before it goes into it. The second major block in the design is the PicoBlaze, which I was just talking about. The PicoBlaze is an external 8-bit microcontroller developed by Xilinx. I use the PicoBlaze to receive and process all the data coming in from the UART interface. I also use it to determine what data is going to be transmitted to the terminal and to inform the user whenever an overflow error or a parity error occurs. The port ID, write strobe, and read strobe outputs go into a decoder that I use to determine the data to write to the terminal and what data to read from the UART interface. The third major block in this design consists of the transmit engine. I use the transmit engine to format the data bits and to determine the parity, the number of bits, and the baud rate at which the transmission is going to occur. After I determine all this, I then shift load this data into a shift register and shift out the data bits individually until all of them have been transmitted to the terminal. The transmit engine also outputs a TX ready flag to let the PicoBlaze know when it's ready to transmit another byte of data. The fourth major block in this design consists of the Recieve Engine. The purpose of this code block is to receive data from the terminal. In order to do this, it needs to first determine the parity, number of bits, and baud rate at which the data is going to be received. After it does this, the data bits are then shifted into a shift register. Once all the data bits have been shifted in, the Recieve Engine then loads the received byte into a register and calculates the parity error. The Recieve Engine also continually updates the overflow flag to make sure that an overflow does not occur. The Recieve Engine outputs both the received byte of data and its status flags, which are overflow, parity error, and RX ready. The received byte of data is then sent over to the PicoBlaze so it can process it and figure out what to transmit to the terminal. Both the receive engine status flags and the transmit engine status flags are concatenated together, and they then go into a multiplexer. This multiplexer decides what 8 bits of data to send into the import of the PicoBlaze based on whether read 0 is set high. If it is, then the import of the PicoBlaze gets status flags. Otherwise, it gets the received byte of data from the receive engine. The fifth and final block consists of the memory interface. In the memory interface, I basically have all the needed code to read and write to and from memory. This block relies on the data coming from the PicoBlaze, which it uses to internally create the signals needed to perform read and write operations from and to memory. The memory interface status also goes into the multiplexer along with the UART status flags and the receive engine data to determine the input data to the PicoBlaze. And that's the gist of how this project works. Alright, so now that I've described all the different aspects of the project, let's test it. I've already synthesized the project. Now all I need to do is upload the bit file to my Nexus 2 board using adept. Let's find the file. There we go, and let's program it. Programming successful. Alright, now let's open up a terminal window. I'm just going to use PuTTY. Let's set this up. So for this communication, let's use a baud rate of 96,000, and let's use 8 data bits, 1 stop bit, and an odd parity. Now that that's set up, let's open up the terminal window. Alright, now I'm going to switch to a view of my board and do the exact same thing over there. Here's my Nexus board. I already programmed the project to it. Now all it's left to do is initialize the system and reset it. This slide switch right here determines how many bits of data are being passed at a time. Off means 7, on means 8. This slide switch determines if we're going to be using parity or not. Off means no parity, on means parity. This slide switch determines what type of parity is being used. Off means even, on means odd, and these 4 slide switches determine the baud rate that we're going to be communicating at. I want to use baud rate of 9600, so I have to make sure that this slide switch is turned on. To summarize, we're using a communication format of 801, and we're using a baud rate of 9600. All I have to do is reset the system, which I map to this button, and we're good to go. Alright, so as you can see, the terminal window displays a banner, and it also displays a prompt, which is an asterisk followed by a greater than sign. Now let's enter some characters into the terminal window. When I enter a character, its data is sent to the PicoBlaze. If the received character is a carriage return or a line feed, then the PicoBlaze has the UART engine transmit a new line command and reissue the prompt to the terminal window. If the character received is a pound sign, then the PicoBlaze has the UART engine transmit my hometown, which, as you can see here, is Porterville, California. Let me just type in some more characters. If the received character is a backspace, which I'm pressing right now, then a destructive delete character is transmitted to the terminal, which deletes a character from the terminal screen. Now I make sure that the prompt does not get deleted when I input a backspace or a delete character. Any other valid ASCII characters that I enter on the keyboard are all echoed. You can also put special characters and numbers, of course. Every character that I type into the terminal is also written to the micron memory located on the Nexus 2 board, starting at memory location 0 times 0, 0. Each address location corresponds to 16 bits of data. Data can be written up to memory location 0 times 200 in the micron memory. Characters that are received after this limit is reached will begin to overwrite the characters previously saved in memory, starting at the beginning at memory address 0 times 0, 0, 0. Finally, in order to view the contents of micron memory that have been written to, all that I have to do is send an asterisk to the PicoBlaze. Let me do that right now. This character causes the PicoBlaze to retrieve all the memory data that has been written to and display it on the terminal. As you can see, here's everything that I've typed out on the terminal, and here is all the saved data. Now this prompt and all of the different processing that's being done within the PicoBlaze is all done using some assembly code that I made for this project. I'm just gonna skim through it real quick because in total it's 742 lines of assembly. So here I'm just declaring all the different letters that I use. Here's all the registers being used. Here's where I check any status flags. Here's where I'm transferring a byte of data over to the UART. Here's where I'm processing all the data that's coming in. I'm seeing if it's a carriage return, a line feed, an asterisk. I'm reading from memory, checking if it's a backspace, a delete, echoing a character otherwise. Here I'm writing to memory. Here's where I'm zeroing out everything in memory. Here's where I display the banner. Here's a new prompt. And yeah, as you can see, it's a lot of repetitive calling and loading to transmit the different letters. That's basically the gist of how the program works. That pretty much wraps up the demo. All in all, this project helped me learn to really appreciate the complexity of seemingly simple programs. Who would have thought that receiving and transmitting characters would take so much work behind the scenes? I sure didn't. Well, at any rate, I hope you enjoyed learning a little more about my UART interface. I sure enjoyed visiting this project. Thanks for tuning in, and enjoy the rest of your day.